Good afternoon, everyone. It's a great pleasure to introduce Lilit Martirosyan from the University of North Carolina. Lilit has spoken once before in our seminar. It is wonderful to see her back today, and she's going to talk about braid rigidity for path algebras.
Thank you, Lisa, for introducing me, and thank you for inviting me to give this talk. It's nice to be almost back in Rutgers in online version. I will talk about braid rigidity for path algebras. This is joint work with Hans Wenzel. And I will start with the exceptional algebra of G2 type, Lie algebra, and G will be the Lie algebra, and V will be the simple 7-dimensional representation. And first of all, I will recall some facts about the basic roots and weights of this Lie algebra. And with respect to orthonormal unit vectors, we can write the roots of it as short roots and long roots. These ones are short roots and these ones are long roots. And we can choose the base to be alpha 1, alpha 2, the short and long root. And the while vector is given by rho. For the while group is the 12-dimensional dihedral group. And the fundamental weights are given by lambda 1 and lambda 2. The following describes the dominant while chamber for G for this Lie algebra. And I will explain why I have the red line in the next slide. So these are all the dominant weights arranged in the lattice. For the smallest non-trivial module, the 7-dimensional representation of this Lie algebra, we will need to know how to tensor irreducible representation with V. And so if V is the 7-dimensional, the weights of this representation are the short roots of the Lie algebra and together with the 0 weight. And we would like to have such a decomposition of the tensor product where V lambda is a simple module. I will describe this decomposition here in the diagram. So if lambda is in one of those blue dots in the middle, then the weights that occur in the decomposition will be the corners of the hexagon centered at lambda and the center of the hexagon as well. And oops, yeah. And if the lambda is on one of those red lines, as you see, or in this case, one corner of the hexagon is missing. And in this case, 2 corners are missing. And in those cases, the decomposition consists of all the corners that are within the wall chamber and the center itself. And if your lambda is on the left side of the wall chamber, then we also omit the lambda. In other words, the decomposition, for example, for this weight will be the 3 irreducible weights here. Irreducible, the 3 weights, the dominant weights here. And so that gives us the decomposition in here. This is what I describe here. And using this, we can draw the Braided diagram from V tensor N. So the V is the 7-dimensional one corresponding to lambda 1, 0 is the trivial representation, and the second power of V decomposes as a direct sum of 4 irreducibles. And you can continue decomposing all the V tensor 3 will be in terms of 6 and etc. And those lines between weights will correspond to the inclusion. So it will correspond that V tensor 2. So if I will explain this later, that if, for example, V lambda tensor V includes 2 lambda 1, then there will be line from 2 lambda 1 to lambda 2. So that's how we describe the Braided diagram. And the following result, has been shown previously by Lehrer and Zhang with different proofs also given by Morrison and separately by me and Hans Wenzel. And we have shown that if V is a 7-dimensional representation of the Dreamfield-Jimbo quantum group corresponding to G2 with highest weight lambda 1, then the centralizer algebra is generated by the image of the braid group in it for Q not a root of unity. So we use very different proofs from the previous results, and in particular, we don't use any computer computations. And more generally, we also show that if V is a 7-dimensional irreducible representation and V is a irreducible representation with highest weight, lambda, then the image of the affine braid group also generates this centralizer algebra. In this case, you notice that one of this one of the modules in the tensor product is arbitrarily irreducible. And by affine braid group, we mean here braid group with one additional generator. In general, this was interesting on its own, but it was also useful for studying categorification of representations. So I will explain what are.
I just want to understand. So affine braid group, you mean one more node corresponding to the affine SLN diagram?
This has one more node for the braid group. So it's a affine braid group that.
For this Coxeter diagram, which is just a circle.
Yes, I think.
Okay. Yeah, so the extra generator kind of braids with both ends.
Yes.
Okay.
So we will talk about lambda to be set of labels with distinguished, any set of labels with distinguished label 0 together with a not necessary symmetric relation. And by a path of length n, we mean a map from 0 to n to lambda such that t0 equal to 0. So it will start at 0, and there will be line from t each consecutive one using this relation defined on lambda. And we will denote by pn's the set of all paths of length n. And we will define by Cn the algebra, so where these are matrices, so m by m matrices, and m nu n is the number of paths of length n that end in nu. So we consider for every weight that you can reach by length n path for every label, then we consider all the paths that you can, the number of paths that you can reach there of length n, and we construct this matrices. And we would like to define an embedding of Cn minus 1 into Cn, so one consisting of paths less of dimension, of size, of length n minus 1. And we will consider the simple modules labeled by nu, Cn modules. And they have a basis labeled by paths which end in nu. And this, and we can decompose these modules into simple Cn minus modules given by the maps t restrict to by 1 less. So t goes to t prime, where t prime is the restriction of t on the length 0 to n minus 1. And hence we have the following isomorphism of Cn minus 1 modules, where we will, mu will here will run over all labels which are the endpoint of a path of length n minus 1 such that you can reach from mu to nu. Okay. And we will define a path algebra corresponding to this label set with the relation to be the sequence of these algebras, which are given by the embeddings. And the standard algebra of a path, example of a path algebra is given by the labeling set that consists of all the Young diagrams with 0 being the empty Young diagram, and you have the relation mu nu if mu is included in nu, and has and you can obtain mu from nu by so it is obtained by adding a box to the previous one. And In this case, each path corresponds to a Young tableau. Here we are talking about standard Young tableaus, which are order, their labels are in an increasing order in each row and column. And in that case, the path algebra is isomorphic to the algebra of the symmetric group. And in general, we will talk about C to be semi-simple tensor category whose home spaces are complex vector spaces. And if you prefer, you can think about this to be a representation category of Drinfeld-Jimbo quantum group or the corresponding semi-simple Lie algebra. And by lambda, we've been labeling set of simple objects where 0 is the label for the trivial object. So in this case, and we will assume that V has this is a simple object with the multiplicity 1 property. In other words, when you tensor it with any other module, then it is a direct sum of mutually non-isomorphic simple modules for any mu. And by the relation, we mean the following. So V mu will be included in V nu will be included in V mu tensor V if there is a relation from mu to nu. And this will allow us to give description of the centralizer algebra via paths. And we have the following direct sum decomposition of objects in C given by, so we can take V tensor N, and this is equal to, we can find these multiplicities from the Bratelli diagram in the small cases. And we have such a description where M nu N is the number of paths of length N ending in nu. And that particularly gives us that the path algebra is isomorphic to this centralizer. Well, Cn is isomorphic to this endomorphism algebra. And we will denote by P and mu all the paths of length n which end in mu. And we can check that the sum of those paths, if you take, is a central idempotent in the centralizer algebra. And we can define a basis for the simple modules labeled by all the paths that end in mu. And here we can let Vt to be the image of Pt for any path that ends in mu. And this is uniquely determined up to scalar multiples. Now, for every 2 dominant weights, we can, with such inclusions, in other words, you can reach delta weight by path of length n minus k and mu by a path of length n. Then by paths, by pk delta mu, we mean the set of all paths from delta to mu of length k. So here I have a picture. And delta and mu will be paths as defined on slide 2 of, yeah, set of all lengths, so path as I defined path previously. And by delta k, wk delta mu, we will be this, the vector space spanned by these paths. And if you fix T to be a path from of length n minus k, then we can think of all the paths here as starting with this path basically and extending to the path from delta to nu. And that way we obtain a representation of V tensor k on this path, on this vector space of paths. And the way we construct it is for every A it will be mapped into Pt tensor A multiplied by Z V tensor N. And here this will act on Wk delta mu, and where we will of course think of every path in Pk delta mu as the extension of it by t. In other words, we start from 0 to delta by t, and then we think of it as an extended from delta to mu to be path from here. And we can use this to act on these paths. So we obtain a representation. Okay. A couple of things about braided and ribbon tensor categories. A braided tensor category has canonical isomorphisms. In this form, they satisfy the following conditions. And similar one for symmetric case. And by B and V mean Artin's braid group with given generators delta I and relations, sorry, sigma I from 1 to n minus 1 and classic relations for Artin's braid group. And one can show that you can obtain a representation of the braid group into NV tensor N as well for any object V in C taking the following map. So CVV will act in the ith position of this tensor powers, where IK is the identity morphism of V tensor K. And using the path basis with the above, we can express the action of sigma I via a matrix in the following way. So in this case, we are considering this representation above we defined on paths, but we are considering for the paths of length 2, and where summation will go over all the paths that are different from I. Only in position, sorry, all the paths S will be different from T only in one position. So only in I position, given sigma I gets mapped into AI. And each of those paths are uniquely, vectors corresponding to paths are uniquely determined up to rescaling, so that way the matrix entries here are also determined up to conjugation by a diagonal matrix. And we have an associated ribbon braid structure, and it is given in the following way. And delta n is an element of the braid group defined inductively. So delta 2 is sigma 1, and we can define consecutively in this way. And it is well known that the square of delta n generates the center of the braid group. And one can show that the ribbon map has the following relation. And if V lambda is a simple object, ribbon map will act on it as by a scalar theta lambda, and center element acts in a simple component labeled by alpha via scalar. If the BN representation labeled by alpha acts non-trivially on the and with tensor n modules, then it follows, we have the following relation from equation 10, where here we identify by V theta V as the scalar with which ribbon map acts on V. We give the following definition for P, a path algebra. We will call a system of representations of braid groups representations of type P if the braid generators act on paths as above. As in this way. So as we defined for the braid generator, so they will act on paths of length 2. Go back. And we will require that the central element act via also fixed scalar on every path of length n, which end in lambda. And we will call the path algebra braid rigid if any non-trivial braid representation of type P is uniquely determined by the image of sigma 1. So we consider path representations of braid groups of type G2 and braid representations for the path algebra generated by the, in other words, braid representations for the path algebra generated by the 7-dimensional representation corresponding to G2 Lie algebra. And we have recall that we can, if we have a representation of BM on the path space, we have the following restriction rule that where with the restrictions summation goes over all mu, where lambda minus is a weight of the 7-dimensional representation, except the 0 weight. For G2, the dominant integral weights are given in this form, and we write lambda equal to lambda 1, lambda 2 for brevity. And dominant weights can be written in this way. And it follows from the decomposition of V tensor 2 that we have 4 eigenvalues corresponding to the sub-representations with those labels, respectively, because we saw that V tensor 2 splits as a direct sum of 4 irreducibles. And we can compute those eigenvalues. So we find that those are the eigenvalues corresponding to those representations. And we give the following requirement. The eigenvalues of rho sigma 1 are as above for Q not a root of unity. And if the representations of B3 are irreducible for all modules W mu 3 and of length 3 paths here, and braid acts as a scalar on each module compatible with ribbon structure. So given by these formulas. And then we have to go back a little bit. We prove the following theorem that any path representation of braid groups of type G2 satisfying the condition stated above is uniquely determined by the eigenvalues of sigma 1. More precisely, if any two such path representations any path representation sigma 1, rho 1 and rho 2 such that the restriction on B2, so sigma 1 coincide, then the representations of Bn on any module are isomorphic. So we show that what we show is that the path algebra associated to the 7-dimensional representation V of G2 is braid rigid, provided that image of the braid group generates B3 generates and endomorphism algebra of B3. And this leads to the classification of tensor categories, and so the classification of ribbon tensor categories whose fusion rules are the ones from G2. And if C is a semi-simple ribbon tensor category whose fusion rules are the ones of G2, and let U to be the representation category of G2, then the following theorem has been obtained previously by Morrison, Peter, and Snyder, and it was shown by me and Hans Wessensel using different methods. And if V is an object in C corresponding to the 7-dimensional representation, assume that the image of B3 generates the endomorphism algebra with tensor 3, then the C and representation theory, this categories, representation category corresponding to G2 is isomorphic, is equivalent to the given category for some Q not root of unity. So this is all I was going to tell for today.
So let's unmute ourselves and thank the speaker.
Thank you.
Thanks very much for the beautiful talk, Lilit.
Thank you.
Are there any questions? So we had some questions at the beginning.
Yeah. I think somebody else should ask questions. I asked a lot of questions already.
So I missed part of the initial discussion. So was this this seemed to be about G2 today.
Yes.
Yeah.
So actually, I do have a question. If I I'm sort of still learning a little bit about quantum groups, but is there a restriction map from UQ07 to UQG2, Lilith?
Could you say it again? I'm sorry.
From quantum group for 07 to the quantum group of G2. Is there a restriction functor for modules?
I believe there is also just in the classical case, but I'm not an expert also.
No, but what I'm saying is that for orthogonal groups, it's some, I mean, is there a functor from which has some nice properties?
I'm not sure actually.
Because when you're looking at invariant theory under G2, you could start with invariant theory for 07.
Right, for the classical cases.
Yeah, because you're taking tensor powers of V.
Right.
For example, so you could think of V as an 07 module, and then you know how it breaks up, and then there is further branching under G2.
Right.
And so there should be some functor, and because G2 is sort of very large in 07, this functor should have nice properties, and maybe you can understand them also at the level of the tensor category. I think you sort of have most of the machinery to do this.
I'm taking note. That sounds interesting.
Yes. I mean, this was my question right at the beginning. So now that
I realized that that's an interesting question. I will think about this.
Yes.
For the last theorem, is it possible to use this to give another proof of the Cauchy-Lewis correspondence between the affine Lie algebra category and the quantum group category? Do you know anything?
That's another interesting question.
Yeah, because you see, I do not know about this kind of the work well, but see, I can see that if you have a category, right? The theorem says that if you have a category satisfy some property, then it must be equivalent to the representation category of the quantum group.
So this gives a classification of the tensor categories with the fusion rules coming from G2, but
yeah, but the Cauchy-Lewis theorem is basically says that if you have a representation category of the quantum group, then see the is supposed to equivalent to the affine Lie algebra category, a suitable category of affine Lie algebra. So if one has this type of theorem, then if one can certainly this is for Q not a root of unity, but see Cauchy-Lewis work also works for the not root of unity.
right.
So if one can verify that some category satisfy these property, then you see at least the category, right? But I think this equivalence means as a tensor category, right?
As a tensor category.
Yeah. So then we do see that the if one can do this, that would be actually a very nice sort of way of this kind of equivalence.
Yeah, I will definitely check that out. Yeah, thank you.
I had a question which may be obvious to people who know more about the theory. I'm sorry? Okay. You can hear me?
Yes.
Yeah. So I'm just looking at the third tensor power appearing in this and wondering, is this related to the fact that G2 can be defined as the stabilizer of a trilinear form? Because I know you mentioned earlier that this method also works for E6, which is also the stabilizer of a trilinear form, but some of the other exceptional groups are not. Is that related to your theory, or is that just
Uh,
a coincidence, do you think?
Actually, we're currently trying to eliminate this condition on the third tensor power. So in our next work, we might not have that one. So this is actually easy to check condition, but we believe that we can eliminate that condition. I'm not sure that it relates to the trilinear forms, but that's interesting. I will think about that.
Are there any other questions?
Yeah, so how important was this this sort of Peary rule that you had? I don't think you'll have that for E6, will you?
The restriction of the
multiplicity free on tensoring with this V, 7-dimensional representation.
So we used those rules of tensoring, sorry, that was further, to obtain the path algebra. And so we used the braid representations acting on those paths. And so that's why we want to know the Braided diagram, and we want to know all these paths and understand how these braid groups act on the paths. And basically inductively we compute the matrix entries of those representations.
Yeah, but you know, the fact that you could start with this smallest representation of G2, and so tensoring with the small representation, it's like, well, I don't know, not even a Peary rule. I mean, it's like just tensoring with one thing, and then you have a decomposition, which is multiplicity free.
Right, exactly.
So this will, I don't think, does this work for the smallest representation of E6?
Oh, I think so. I think for E6 is 7, for the vector representation, it works, not the smallest one, I believe. It's the vector representation.
Vector represent, you mean the adjoint representation? What's the vector representation of E6?
Yeah, for the adjoint representation.
It does not work for the 26, but it works for the adjoint representation.
I believe so. For the classical cases also similarly.
I see. Okay. Yeah.
Well, let's thank Lilit once again.
Okay.
Thank you.